today, but want to recap what we looked at last week because we've already seen logs and exponents are related, so their functions are also going to be related. So last week, we looked at something of this form. At the end of last week, right? Y equals a times b to the x. Okay, this is called an exponential function because the variable is in the exponent position. Okay? Now, as an example, if we look at y equals 3 times 2 to the x. Actually, no, I'm going to make it simpler. Let's say 1 times 2 to the x, which is just 2 to the x. Okay? So if we make a really quick table of values, -2, -1, 1, 0, 1, 2. Okay. If x is -2, this would be 2 to the -2, which is 1 over 2 squared, 1/4. I'm going to go quite quickly here because we already looked at this. This guy would be 2 to the -1, which is 1 over 2. This is 2 to the 0, which is 1. 2 to the 1 is 2, and 2 squared is 4. So we looked at that. We also compared it to this. Whoops, sorry. Okay, so I'm taking the reciprocal, essentially, of the base 2. And I want to kind of see what happens in this table of values. Okay, so here, let's take the same x values, -2, -1, 0, 1, and 2. And if I have here 1 times a half to the x is just a half to the x. So this is going to be a half to the -2. And that is equal to 2 squared, because you can flip this and make it positive. I'm essentially bringing this up. And that is 4. Okay? And then this would be a half to the -1, which is just 2. This is a half to the 0, which is 1. This is a half to the 1, which is a half. And this is a half squared, which is a 1/4. Okay, so I'm going quite quickly here because we did go through this last week. What ends up happening, though, when we compare these two graphs is they are quite related. And in fact, you can probably see from the table of values that the y values kind of swap, right? When x is negative values here, it's the opposite. 4 is the y value for when x is 2 here. Okay, so what we end up getting, -2, -1, 0, 1, 2, is here when x is -2, y is a 1/4. Here it's a half. Here it's 1. Here it's 2. And here it's 4. So this looks like this. Does that look familiar? Okay. And then the other one I'll do in red. It's going to have a similar shape, but now the negative x values correspond to the y values here when they were positive. So when x is -2, y is 4. When x is -1, y is 2. When x is 0, y is 1. When x is 1, y is a half. When x is 2, y is a 1/4. So these kind of go the other way. Okay. And what we found, we looked at a couple of examples of these functions. What we found is that when that base value is larger than 1, you keep increasing. So you get bigger and bigger and bigger and bigger and bigger because you keep multiplying by something bigger than 1. So that's what we see in the black graph. As x gets bigger, y gets bigger too, as well, because we keep doubling and doubling and doubling and doubling. But when we multiply repeatedly by something that's less than 1, and specifically between 0 and 1, and we keep doing that over and over and over again, keep having something and having, we're going to start to get really, really, really small. Okay? So really what we were interested in when we look at this function here is we're especially interested in the base value because that tells us what the shape of the graph is going to look like. Is it going to look like the black one or is it going to look like the red one? Okay? So that's one thing that we considered. If we just have y equals a times b to the x, right? So we looked at these base values, and if we saw that the base is greater than, not 0, if the base is greater than 1, then we got this picture. And if the base was between 0 and 1, we got this picture. Whoops. There we go. Okay, so that was one thing we were really interested in. The other thing that we were interested in was the a value. And where did the a value show up on the graph? It's kind of hard to see. Yeah? Sorry?
The y-intercept.
Yeah, exactly. It's the y-intercept, right? So here, the a value is 1. That was the y-intercept. And it's 1 here as well. That was also the y-intercept. So a is the y-intercept. Okay? So this is just a summary of what we've already seen. Okay? Now, I'm going to go in a slightly different direction here. And I am going to take a look at this function. Y equals 10 to the x. Okay? And what I'm going to do is right beside it, I'm going to swap x and y. So if I swap x and y, it's actually called an inverse function. You guys don't need to know that, but that's a thing. If you swap x and y, then the x is going to go there, so you're going to get x equals 10 to the y. Okay, so far so good? Okay, now what I want to do is take this guy and write it in logarithmic form. Okay, so if I'm writing this in logarithmic form, what would the base of the logarithm be? It's the base of my logarithm. 10. I'm going to put the log part on this side. So log base 10, what's the value that should go in here? Of x equals, what should go here? What's the exponent? Yeah. So this is called a logarithmic function. And a logarithmic function is related to the exponential function by swapping the two variables. We essentially swap x and y, write it in logarithmic form, and there's your logarithmic function. Okay? So this is a logarithmic function. Okay? So in terms of what does it look like? Okay, so what I need you guys to do now is get some scrap paper that you're willing to cut up and throw away. And if you need some, I have some here. Anyone need some? Okay, I'm actually going to split these in half because you don't need a whole piece. If you have some scrap paper, great.
I'm good.
You're good?
Yeah.
Okay. There you go. You have? You're good? Okay, you guys have. Awesome. Anyone else? Everyone else has? I have one sheet left, although I could make more. Okay, well, I will use this one. Actually, I'm going to use a big one so that you guys can see. Okay, so here's what I want you to do. You need, like, if possible, a pen and a pencil. A pencil is an absolute must. You gotta have a pencil for this activity. If you have a pen as well, that's great. So what you're gonna do if you have the pen is with the pen, you're gonna draw a coordinate plane, like that. Okay? So actually, I'll put this on here as well, just so you guys can see. Here's your paper. And with pen, you're going to draw that. Okay? And then what I want you to do in pencil, must be in pencil here, is I want you to draw this function, y equals 10 to the x. So that's going to kind of look like, okay, the y-intercept is 1, right? The base is greater than 1. So it's going to go like that. It doesn't have to be all that close. But you got to do it in pencil. And then once you get it in pencil, okay, so here's mine. It's not super pretty, but there it is. Once you get it in pencil, this is the most important part, okay? You have to color over that pencil and like almost destroy the page. You need to make it super, super thick. So put all of your arm energy in there and just, I'll show you what I'm going to do. So I'm doing this. Okay, so that's my start. Okay, so just make that super, super thick. If you need a pencil, I've got a bunch up here. Okay, so you're going to make that thick. And now what I want to do is when you swap x and y, you're basically graphically doing a reflection in the line y equals x. When y and x are equal, then when you swap them, you get the same thing, right? If you have the 0.22 and you swap them, you still have the 0.22. So when we swap x and y, which is what we're doing to get the logarithmic function, we're reflecting in this line. So this is a line of reflection. Okay? Now, when you're doing this on a paper, do not just do the diagonal. Because you can see if I do the diagonal, my axes are not on top of each other. When you do this, and that's why it's kind of helpful to use the pen, you want to fold so that the horizontal axis kind of lies on the original vertical axis. So if you hold it up to the light, sometimes it works a little better. There we go. You really want to fold on the diagonal. So it's not going to be the diagonal of the page because we're using rectangular paper here. Oh, that's not even that good. Hold on. I can do that better. There we go. Okay, there we go. That's better. Doesn't have to be perfect, but if you can make it as close to lying on top of each other as you can. So when I hold this up to the light, I can see the axes are kind of lying right on top of each other. Okay? And once you do that, you're going to put the paper down, and you are going to, with your hand, like press really hard over the pencil that you drew. Because you kind of want to rub it off. Press really, really, really hard. And then open it up, and you should see the reflection. So it's kind of faint on my page, but the reflection looks sort of like this. Oh, do this in a different color. This is the reflected image. That's what it looks like. Okay? this is the function y equals log x, log base 10 of x. It's a reflection of the exponential function in the line y equals x because we are swapping the two variables. Okay, so we looked last class at what is like the domain of the exponential function. What's the range? What is the end behavior? All that kind of stuff. All of that's going to swap, right? Not the end behavior, but the domain of the exponential is going to become the range of the logarithmic. The range of the exponential is going to become the domain of the logarithmic because we're swapping the two variables. This is the overall shape of these logarithmic functions, okay, and how they are essentially related to the exponential function. So let's go now on to page 67 at the bottom. And I apologize, my printing is off throughout this whole unit where, like, I guess I must have pressed the space bar, but this actually goes in the other, on the other, in the next, top of the next page. So we are going to basically try graphing all of these on our calculator, okay? The form of a logarithmic function is y equals a times log base b of x. And they will all take that overall shape that we just did when we did this little activity, okay? So one thing that you do have to consider if you are entering something into your calculator is that your calculator only uses base 10. So if you have a logarithmic function that does not have base 10, you have to use the change of base law to enter it in. Okay? So change of base law, remember, you go log over log, and that new base is 10 because we want to enter it into our calculator. What goes in the numerator? 2x. And in the denominator is the 5. Okay? So that's how we'll enter it into our calculator. For the second one, we're fine because it's already base 10. And for the third one, this is going to be -5 times, again, log over log. In the numerator is the x, in the denominator is the 2. Okay, so I'm going to pull out a calculator, and we will just quickly graph these, and maybe we'll sketch them down, and then we'll see how much time we have left. I don't know how much time we're going to have left. Okay, waiting for this to open. All right, so here we go. I'm going to turn off my plot, and I'm going to clear this and clear this. So the first one was log of 2x divided by the log of 5. Okay. The second one was just 12 times the log of x. That's already base 10. And the third one is -5 times, you don't have to put the times in there, but you can if you want, log of x divided by the log of 2. And I am going to just set my window to the standard setting. So that's zoom 6, -10 to 10, and -10 to 10. Okay. So I'm going to go on to the next page, and we'll sketch these. Oh, shoot. Okay, there we go. Actually, you know what? We'll do them one at a time. So not all on the same graph. So I don't have to erase these, but if you just unhighlight the equal sign, it'll just graph one at a time. And on the Casio, you can select the graphs that you want to graph. And now we'll just look at this guy. Okay, So that's kind of interesting because when we did that paper folding technique, kind of looks like this cuts out right there. And there's no line that goes down that sort of hugs the y-axis. Okay? So what I actually want to do is let's change the domain. I want to stretch this out, essentially. So I am going to change the window settings so that my x-min is maybe 0, and my x-max is 1. And then I'm going to graph it. Okay, and you can see it actually goes down a little further. And now I'm going to stretch this out a bit. So I'm going to make it, instead of the max being 1, I'm going to make the max 0.1. And you can see it's going down even further. And if I do that again, 0.01, you guys don't need to do this along with me. It keeps going down. This little end looks like an endpoint, keeps going down further and further and further. Okay? Let's talk about what's actually going on there. What's going on there is that there's a vertical asymptote. But it looks so much like a vertical line that your calculator will not graph it, because these calculators will only graph functions, and a vertical line is not a function. So you need to know that there is, in fact, a vertical asymptote. It's going to get infinitely close to the y-axis but never touch it, even though when you graph it using technology, you may not see that. Okay? So I'm going to go back now to the standard setting. And that's something you got to know. So here, that first graph, oh, what happened there? Looks like this. There is, in fact, a vertical asymptote there. And I think we'll leave it there for today. We'll pick this up tomorrow.
Reminder to students that if you were absent for block 1 this morning and you're in grade 10 or 11, the course registration forms were